Okay, moving on to chapter 4, and this is what we're going to talk about this chapter. We're going to talk about limiting reagent, how to balance equations, and these types of things, so stoichiometry. And question for you, does your car run on air or gas or fuel? And I've gone ahead and balanced this equation. So we have two octanes. It depends on the gasoline, but saying it's pure octane. So we have 2 octanes plus 25 oxygens makes 16 carbon dioxide and 18 waters. So I've already shown here 114 grams per mole for the octane, so 228 grams of octane, 800 grams of oxygen, forming 704 grams of carbon dioxide and 324 grams of water. And or 1,028 grams of reactants forms 1,028 grams of products. So from this, it really seems like your car runs on air, on oxygen, more than it does on fuel. And but you don't really think of that when you're driving your car around because there is just so much more oxygen in the atmosphere than there is fuel. So what you're actually limited by is the fuel. And where you do have to worry about this, though, is in outer space. So if you're using the chemical reaction for thrust in a rocket, you have to carry the oxidizer with you. So it's a little different when you're in space. And also in certain vehicles, although we don't run the space shuttle anymore, there was liquid oxygen that would mix with the hydrogen in the main engine for the space shuttle. And just a couple other things. Notice that you have 200 grams of octane making 700 grams of carbon dioxide. Why is this so much more? Well, it's because of the fact that carbon is 12 grams per mole, but CO2, carbon dioxide, has 44 grams per mole from the 2 oxygen, so adding on that extra mass for that. That could become important later if we do end up taxing carbon, but as you burn things, the mass of carbon coming off is quite high because of, well, the carbon dioxide is higher. It's because of the oxygen with that. Okay, but moving along, you will know how to do all this soon as you complete this lecture or in the content therein. So let's start off with how to balance chemical equations. So this chemical equation is balanced. We have 1 part methane CH4 and 2 oxygens reacting to form a carbon dioxide molecule and 2 waters. And notice that there is the same number of atoms on both sides. So here in the black, there's 1 carbon atom on both sides. There are 4 hydrogens, 1, 2, 3, 4 on the left, and 4 on the right. So, and then there are also 4 oxygens. So 4 oxygens there, 1, 2, 3, 4. Each one there, and I do apologize if anyone's colorblind. I'm trying to illustrate that with these, but usually people can tell by the grayscale even if you are colorblind. Okay, so what is the procedure for balancing equations? Well, you have to pick an atom and then go through and make sure that there is the same on the reactants and product side, and then continue on through and then multiply through to get whole numbers, because there can't be half numbers. So let me give you an example here. C4H10 plus oxygen makes carbon dioxide and water, simple combustion reaction. So start with carbons. There are 4 carbons in the reactants, so let's put 4 carbons in the products right there for CO2. Now let's balance the hydrogens. There are 10 hydrogens on the left, so we need to have 5, and this 5 times 2, because H2O, so the 5 waters is in fact 10 oxygens. So now let's balance the oxygens. And we have 2 on the left, and how many we have on the right? We have, for this carbon dioxide, 4 CO2s, there's 8 oxygens, and then there's 5. So we have 13 oxygens That means we need 13 halves O2, but that's not proper. So what we have to do is we have to multiply the whole equation by 2. So multiplying by 2, then this brings us to 13. Then this brings us to 8 and 10. So now let us go and check out how let's check this, see the right amount. So 2 of the C4s, that means on the left we have 8 carbons and we have 8 CO2s. The 1 is implied in the carbon, so we have 8 carbons on both sides. Hydrogens, we have 20 hydrogens on the left, and then we have 20 on the right. Now looking at the oxygens, we have 26 oxygens from the 13 O2s. And then so 8 times 2 is 16 plus 10, that's 26. So 26 oxygens on both sides. This equation is balanced. So it has the same number of atoms both. So one thing you can't do when you do chemical equations, you can't change the molecules. Oops. You can't go ahead and change a molecule. So you can't say, well, you know what, instead of doing that, what if I just put O3 there? That'll solve my problems. No, you can't do that. If you do that, then you change the compound. Adding another atom will change the compound. Okay, so let's see if we can do this. How many waters are there in this balanced chemical equation? So go ahead and pause it if you want. If not, and try it yourself. If not, I will work on this and show you. So I would start with the carbons, 6 carbons left, 6 carbons to the right. Well, we already see there's a problem because we have an odd number, so we have to put a 2 here to get the waters. So 2 there, so that means we're going to have 12 CO2s, and this means we're going to have 13 waters. That's already going to be an odd number, so we're going to have to multiply these all again by 2. So this is going to be 4, and this is going to be 24, and this is going to be 26. Then for the oxygens, then we're going to have 37, like so, to get the right number on each side. So how many waters? It's 26. Okay. So next thing I'm going to do is I'm going to talk about limiting reagents. And I already mentioned that with the car, right? You drive your car, and really what you're limited by is the amount of fuel that you have. So, but let's go back deep into our childhood and how to make a Happy Meal. So, what isn't a Happy Meal? You have a burger, fries, drink, and a toy. I don't know. I think when I do this in class, people say all these things like apple slices and stuff. I lived a very unhealthy childhood, okay? That's what you should come from this. I had an unhealthy childhood with burgers, fries, sugary drinks, and toys that could choke me. So that's the way it was in the 80s. Okay, but let's say we have 1,000 burgers, 10 fries, 1,000 drinks, and 500 toys. How many Happy Meals can we make? We can only make 10. Why? Because we are limited by the fries. So you are limited by something. In this case, it is the number of French fries. So in order to make more Happy Meals, you need to have more fries. And what if you write corporate and they send you 1,000 toys? You still can't make any more Happy Meals because you're still limited by the fries. So what's nice about a Happy Meal is that they're all 1 to 1 to 1 to 1 ratio. What about a ham sandwich? And here's my ham sandwich equation. We have 2 slices of bread and 1 slice of ham makes a ham sandwich. Very simple ham sandwich. If we have 1,000 slices of bread and 1,000 slices of ham, how many ham sandwiches can we make? We can only make 500. And the reason is because of this 2 to 1 ratio of the bread to the ham. So we need to have twice as much ham I'm sorry, twice as much bread to make a ham sandwich, and we are limited by that. So that's important when we get into stoichiometry because depending on what species you're looking at, it may limit you. It may not be as obvious what the limiting reagent is. Okay, so let's start with a real simple one. Stoichiometry. During photosynthesis, plants convert carbon dioxide into water and glucose according to the photosynthesis reaction. Say a particular plant consumes 37.8 grams of carbon dioxide in 1 week. Uh, what mass of glucose is made there? So assuming there's more enough water, what mass in glucose did it plant synthesize? Okay, and we are doing experiments like this because we want to look at sequestering carbon dioxide. But let's do this. This case, the limiting reagent is telling us we know that carbon dioxide is the limiting reagent. So this has already been told to us. So it's going to be more complicated than the next one, but let's go ahead and do this. So we have 37.8 grams of carbon dioxide, and then mole carbon dioxide to 44 grams carbon dioxide. I'm getting that from 12 from carbon plus 2 times 16 for oxygen is 44. And here is a new step for you. We have a mole of glucose to 6 moles CO2. And that comes from the ratio here in the balanced chemical equation. So this is one of the reasons why it's important to make sure that the chemical equation is balanced properly, because if this is the wrong ratio, you will get the wrong answer. And then last step, 180 grams of glucose, C6H12O6, per mole glucose, C6H12O6. So if you go and you calculate that all out, you get 25.8 grams of glucose. I'm going to GLU. I should have done this before. GLU is the shorthand symbol for glucose, C6H12O6. Okay, a recap for this one. This is a limiting reagent problem. We are given that we know that a plant consumes so much carbon dioxide per week, and we know that it's doing it via this photosynthesis reaction. We already have it balanced. We want to know how much of the product is being made from this reaction, the mass in grams. So the new step, it should all be normal for you. This is the new step here, and that comes from the balanced chemical equation. That way you convert moles of something from, in this case, a product from the moles of reactant. It doesn't matter what you're looking at. We'll just make sure it's balanced and make sure you are using the proper ratio. Okay, so let's go into a little more. Oh, okay. I guess before that, let me talk about limiting reagent and theoretical yield. So limiting reagent, this is the ammonia synthesis reaction. This is a very important reaction. This is where we get our fertilizer from. And it's usually used as an iron catalyst. So we have nitrogen plus 3 hydrogens make 2 ammonias. And so we have a flask here. What's the limiting reagent and which one is in excess? So first of all, here is, let me write the equation. So you have N2 plus 3 H2s make 2 NH3s. What's going to happen? Well, you have 2 nitrogens here, so which means we're going to have 4, it's an H. We're going to have 4 ammonias, and the hydrogens here, so these 2 nitrogens, these are going to use 6 hydrogens, and we have 1, 2, 3, 4, 5, 6, 7, 8. We have an excess of hydrogens, So we're going to have 4 ammonias, and we're going to have 2 hydrogens left over with that. And if you see these other flasks, if you look at flask A here, it's not done reacting. All the nitrogen did not react. And for part B, flask B, it doesn't have the excess hydrogen. Flask C shows the excess hydrogen there. So in this case, the nitrogen is the reactant excess. Okay, and this is in fact how we synthesize ammonia, not in Erlenmeyer flask. We do it in high pressure systems over an iron catalyst. But let's look at this. Ammonia can be synthesized by this reaction. 2 nitrogen monoxide plus 5 hydrogens makes 2 ammonias and 2 waters. So what is the theoretical yield if we start with 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen? So what is the theoretical yield? How much can we make? Oh, well, this is one thing. You have no idea. Just looking at this, you don't know what the limiting reagent is. Let's go ahead and look at this. So we have 86.3 grams nitrogen monoxide, and we have 25.6 grams hydrogen, and then we have mole NO so nitrogen, so 14 plus 16, this is 30 grams NO, and then we have 2 moles ammonia to 2 moles NO. You can just drop the 2 and do 1 by 1, but I'm just writing it there for emphasis so you know that I got it from the balanced chemical equation. For hydrogen, we have mole hydrogen to 2 grams hydrogen times 2 mole ammonia to 5 moles of hydrogen. And looking at this, we can determine that, let's see, where are we? That this will make 2.88 moles NH3, and this will form 5.07 moles NH3. So which one do we pick? Do we pick the high number or the low number? And you pick the low number. So you're limited by something, you're limited by the lower amount. So this is the one we pick, and then we just multiply it. So then this is 17 grams ammonia per mole ammonia, and this is 49.0 grams ammonia is the final answer. Okay, so recap with this one. So we have this chemical reaction. We're starting with 2 different masses of 2 different reactants, and we need to figure out the theoretical yield. So what we do is we look at each reactant and we multiply it as much as and assume it goes to completion. And what we find out is that the nitrogen monoxide produces less ammonia than the hydrogen does. So that means that the nitrogen monoxide is the limiting reagent, and then we go on further and see that that would generate 49 grams of ammonia. So this is your turn. 100 grams of oxygen, 100 grams of hydrogen react. How much water will form? And the balanced chemical equation for this is 2 hydrogens plus oxygen yield 2 waters, like so. So pause it and try it out, see what happens. Okay, so some hints. We have 100 grams O2, mole O2, 32 grams O2, 2 mole water, per mole O2. And if you want 18 grams water per mole water. And hydrogen, 100 grams hydrogen mole H2 to 2 grams mole water. I know it's 2 to 2, but you can simplify it to 1. And here you get 112.5, and this is 900. So which one's the limiting reagent? It's oxygen. How much is formed? It's B. And this is another case where you can apply logic, where B is the only viable answer, really. Because if you look, if you start off with 200 grams of reactants, the most you can make is 200 grams of products. You cannot create matter, so 900 is wrong. Okay, so D is the wrong answer. And in this case, since you have 100 of both reactants, you're going to have over 100 grams of product, so A is wrong too. And it's unlikely that they would be exact ratios, especially at 100 grams, so it's B is really the only viable answer with that. But this is the one I get the students hit me a lot with. If you start out, if you're creating matter in the chemical reaction, then you definitely know that you're wrong. So keep that in mind. Okay, so let's go on and talk about this one, titanium metal from its ore. Okay, so this is how we get most of our metals from, is cracking ore, usually reducing it with carbon. There's other ways you can do it. Aluminum is an example of something. Aluminum we get through electrolysis. So aluminum uses quite a bit of electricity to generate aluminum, but iron, titanium, most other things, gold. We can get by depends. There's a couple different ways you can find the gold just in its native form, like panning for it or finding nuggets, or typically what's done in the United States, we find it in small concentration in rocks, and then we dissolve it with cyanide, and then we extract it chemically from the cyanide for that. They do it illegally in the Amazon by taking mud and dumping mercury in the mud, and then the gold is absorbed in the mercury, and then they take a blowtorch and they boil off the mercury to get the gold. That's a very bad way to do it, but people still do it that way. That's for gold, but most other metals we get this way, and it's important that we use metals for things because we use metals in so many different applications, right? I guess I don't know what age we're in, if we're in the age of silicon or the nuclear age. I'm not sure what age you would call us in, but certainly beyond the Iron Age. But okay, so the other thing about this process, notice that we're having, we're using 28 kilograms of carbon and 88 kilograms of titanium dioxide. This is known as a pilot plant. Okay, so a pilot plant is in between mass production and a small batch. So let's say you're making cookies. So what is a pilot plant? What does it do? So let's say you're making cookies at home. So if I'm going to make cookies at home, I'm going to use my oven, and I'm going to make the cookie dough in a bowl, and then I'm going to put the cookies in a tray and put it in an oven, bake it, and come out and eat the cookies. Is that how they make cookies everywhere else? Like if you're going to go and have a huge, say you're making 10,000 cookies a day, is that the way you make cookies? No, you don't. You have a machine that mixes up the batter. Then you have like probably something that extrudes the right amount of like little cookie things, and then it probably runs on a tray through an oven, and then the cookies are done by the time it runs through the oven. Kind of like that's like mass production. Then there's an in-between state called a pilot plant, because if you're learning how to make the cookies, and if you make a mistake, you're losing a lot of product. So what they do is they make a smaller type of machine that you can learn and tweak and make the mistakes on that, and then that will do much better from the scale up because recipes are usually made in a batch, in a small batch, and then there is a big problem to figure out, okay, now that we've made this in a small batch, how do we make it in massive quantities? So I'm using cookies as an example because I know how to make cookies. Let's say you're making a drug and you finally figure out, you get in the laboratory, you synthesize this drug, and then you figure it out what it can use. Okay, now that I've made this drug, I can make 50 grams in the laboratory. How do I make 20,000 tons? That's a question. You're like, and now we have to find a new way to make this. And one of the ways that's the in-between state is what I said here is a pilot plant. If you live on Maui and you go to the Krispy Kreme, they have a donut factory there. That's kind of what a pilot plant looks like. That's really cool. I love watching that thing, watching them making those glazed donuts. That's making me hungry. Okay, so if you wonder what this is a pilot plant. And from this, we're going to see, you see that it says we have carbon reacting with the titanium dioxide, the rutile is titanium dioxide, reacting with the rutile to form product. What is the limiting reagent and what's the theoretical yield? Why wouldn't we get 100%? Like, well, because you're getting the stuff from the ground. You're digging the stuff up from the ground, and then it's going to have impurities in it. So the impurities that come off, that's also known as slag. It's usually calcium, magnesium silicates, the slag there, and those are the impurities that are in the material. So we don't have pure substances very frequently in nature. So this is going to have other stuff in it. That's the reason why it's not 100%. Okay, so this is the limiting reagent problem. Let's go ahead and do this. So we have 28.6 kilogram carbon. So times 1,000 grams per kilogram times 12.01 grams per carbon per mole carbon. I should use the boxes. Oh well. Then we have, we have mole titanium to 2 moles carbon, and same thing for the rutile. We have 88.2 kilogram titanium dioxide, so 1,000 grams per kilogram. And titanium dioxide is, I'm going to cheat and look this one up. I got this backwards. Nice thing about the iPad. And my unit's in the wrong place. Sorry about that. Mole TiO2. And TiO2 is 79.87 grams TiO2. And this is mole titanium to mole TiO2. And in doing so, we find out that this is equal to 1.19 times 10 to the third moles titanium, and this is equal to 1.10 times 10 to the third moles titanium. Okay, so we know now that this one here is the limiting reagent. So then we just multiply, so then we can go through, and then we have 47.87 grams titanium per mole titanium times kilogram to 1,000 grams. and we get 52.9 kilograms titanium. Okay, so this is our theoretical yield. So I'm doing this in yellow. So 59.2 is our theoretical yield. And our limiting reagent, I did in red. So limiting reagent is the titanium dioxide theoretical yield. Yellow is the 52.9, and I guess I'll do blue for the percent yield. So the percent yield is the actual yield over theoretical yield times 100%. So percent yield, this is going to be the actual yield, which is given to us 42.8 over 52.9, and then we find then times 100% is 80.9%, and that is your percent yield. Okay, so recap with this one. We are given two reactants, and then we went and found the theoretical yield from that, and we were given the actual yield, and then we went through and found the percent yield based off of that. Now, the other thing to notice from this is an example of the chemical engineer, whoever was running this plant, this pilot plant. This person should get a gold star and a big pat on his or her back, because whoever did this did a great job. Because if you look at this, you're using about the same amount of products. So if I was a plant manager and I got these results, I would go and I would try to promote the person that was running this experiment. Because look at this, right, you're running a plant and raw materials cost money, and you used about the same amount of both. But if you look at this, the limiting reagent is the ore, which is more expensive. Ore is much more expensive than the carbon. So whoever was running this picked the more expensive thing to be the limiting reagent and had the cheaper stuff in excess, the cheaper reagent, but it wasn't a huge amount in excess. So it wasn't like the person was using a huge amount. And then that means that for me and my plant, I'm getting as much product as I can from those reactants and doing it cheaply. This is another example of green chemistry. This is efficiency. This is doing things properly, using in that way, using the expensive, harder to obtain mined titanium dioxide versus, I guess, the carbon coke. You can get that from coal, which is also mined, but it's much easier to obtain than the ore. So this person is doing a great job. So pat on the back, theoretical pat on the back, whoever imaginary person was doing this. So let's see if you can do this one. 50 grams oxygen and 850 grams of hydrogen react to make 50 grams of water. What is the percent yield? And if you haven't noticed, oxygen is the limiting reagent. So why don't you try this out? Okay, so I did this one on purpose. If you look at the 112.5, this means that, 56.25 grams of water is the theoretical yield. You can calculate it if you want, but it's just half of the earlier one. So you have 50 over 56.25 times 100%, and I believe that's 90% there. Let me, thing is my phone calculator is in the fritz right now, so let's see here. 50 divided. Yeah, and that's 88%, so that is about 90%. Okay, so went through this quickly, but I was hoping you could go through and repeat it if you need to. So as always, let me know if there's any issues, and I will see you for the next chapter.